All right. Hello, everyone. Welcome to your next class today. I'm James. This is Ananya.
Hi.
I work at the Delphian School. She attends the Delphian School. We both love space.
Yes.
We both love science.
Definitely.
And we both love space science. That kind of goes together. And we're going to be talking today about how rockets are made. You can see behind us in this totally not green screen an image of the space shuttle. We're not going to be talking about the space shuttle exactly, but there's a lot of elements to what you can see back there that we're going to be talking about today. And I have been learning a lot in the last couple of weeks about how rockets are made. I'm excited to share that with you.
Yay!
How much research or personal knowledge do you have already about how rockets are made?
I would say I know like the basics, but I'm not like, I haven't super researched it.
Okay, well, the answer to that is going to be different 40 minutes from now.
Awesome.
Good. Hello to everyone that's joining us. Let me pop into the Q&A section here really quick. A lot of familiar names here and some new names. Welcome to everyone. Go ahead and put in the Q&A section where you're from. I would love to know how many parts of the country and of the planet are represented in this class today. Tanisha says that she saw the Neowise comet on Tuesday. We couldn't see it with our own eyes, but we used someone else's huge telescope. Have you seen this comet?
Yeah. We went to go see it on Friday, and I could actually see it with just my eyes, but it was like pretty faint.
Mm-hmm.
I think it was covered by some clouds on Friday.
Yeah, you have better eyes than me. You could see it easier than I could. And it does look like, if you in this class have not seen it yet, please go out tonight, tomorrow night, as soon as possible, and see it with your own eyes. It's starting to get fainter, so we're kind of losing our window. But hey, if you don't see it now, it's okay. Just stick around. It'll be back in 6,800 years. You'll see it then. The person behind the camera is literally rolling their eyes at me. All right, we have representatives from Canada and Massachusetts and Indiana and India.
Yeah, India.
And California and more Massachusetts, Springfield, Virginia. I lived there for a year. Mexico, LA, all over the place. Wow. Hello, everyone. Toronto, Canada, in the house. Excellent. So let us talk about how is a rocket made? First, though, if you follow the Delphian School's Instagram stories, you saw a question from me posted on there yesterday. What is this image? What does it mean? Why is it important? Do you know?
No.
This is brand new. This is like, if you were reading science journals yesterday, you would know about this. And all of you are going to know about this too right now. This is a historic picture. This is the first ever image of a multi-planet system around a sun-like star that we've ever taken. This was captured by the European Southern Observatory's Very Large Telescope. If you are a constant viewer of these space science classes, you know I've talked about the Very Large Telescope before. Do you know what the official name for the Very Large Telescope is?
No idea. I have no idea what you're talking about.
It's called the Very Large Telescope. That's the official name.
Actually?
Yeah, the VLT, Very Large Telescope.
Wow.
Yeah.
Unexpected.
They didn't, I guess, they were like, that's a good enough name for now.
Wow.
There is a successor that's coming, and it's going to be, they're working on the design and building of it now, and it's going to be extremely large. Can you guess what they are going to call this telescope?
Maybe extremely large telescope?
That's exactly what they're calling it.
There we go.
That's exactly what they're calling it. So I think that it's a very accurate name. So here here's this sun here. And this is a very, very young sun. This is a very young star. This star is only 17 million years old.
Wow.
It's a baby. Our sun is 4.5 billion years old. This thing is a newborn. And there are two large gas giants orbiting it that are still very hot from, it's very early in the process of this solar system being formed. Mm-hmm. So we can still see it with our telescopes.
Do you think those are going to turn into what Earth is now?
No, these are too large. There are probably Earth-like planets being formed around this sun right now.
Okay.
But what's happening is this one is 15 times more massive than Jupiter.
Wow.
It's huge. And it's really, really hot right now. It'll cool down. That's 15 times more massive than Jupiter.
Wow.
This one is much, much smaller. It's only 7 times more massive than Jupiter. So, you know, it's a pipsqueak. And these are not close to their star. If this is a model of our solar system on the inside, that yellow ring, that's the orbit of Pluto.
Wow.
Which is not a planet. But it still exists. So that's the orbit of Pluto around our own sun. This is how far away those 2 planets are from their sun. They're extremely far away. So I nerded out when I saw this article yesterday, and I wanted to share all of it with you. This is a first. This is, you know, the first of many times that scientists will be able to directly take a picture of more than one planet around another star.
And how far away is that system?
I'm glad you asked that. And I have notes on that.
Oh, cool. Okay.
This is me stalling as I pull up my notes on a separate screen. Wow, that is, pardon me just one moment. I just need to zoom in here. Zoom, go closer. Thank you. All right. I was prepared to answer that. Okay, this sun, which is known by the super simple name of TYC 8998760-1.
Wow, rolls off your tongue.
Just like that. It's 300 light years away.
Oh, wow.
So pretty close, actually. It's pretty close to us. All right, so before we start talking about Isaac Newton, I'm going to pop out. I want to catch up on the Q&A section because I know there's people talking here. We have people from Brisbane and from Edmonton, Canada, and some more Toronto. Wow. Okay, good. So thank you so much for joining us from everywhere. So let's talk about rockets and how rockets are made. But first, why rockets? We need to get to space. No, we want to get to space, okay? Because it's fun. We want to explore, we want to learn new things, and it's tough to get up there. I think that's why humans want to go.
Yeah, that makes sense.
You know, it's like you see a tall hill, you just gotta climb it to find out what's up there. What does it look like on the other side? So Isaac Newton said every action has an equal and opposite reaction. This was one of the basic laws of physics that he figured out after he got hit in the head with an apple. So that's very simple, and you can demonstrate this in many ways. You push down on a seesaw and the other end goes up, right? Action, push down, reaction, it goes up. Or you're standing on a boat like I was in the pond the other day, and you go to step off the boat, you are gonna go this way, and the boat is gonna go this way, out from under your feet. You're gonna fall into the water, and it doesn't look cool. That may or may not have happened. Here's a very basic picture of what's happening with a rocket, okay? You have air in a balloon, the air rushes out of the balloon going down, the equal and opposite reaction as the balloon goes up. And we can just substitute the picture of a balloon with the picture of a rocket, and it's the same thing, right? You have these hot gases shooting down, rocket goes up. Everyone tracking so far? Yes?
Yes.
Excellent. It's about to get more complicated, but that's okay. We are going to be talking about one particular kind of rocket today. Someone asked in the class the other day, on Monday, they said, I want to know how rockets are made.
Cool.
There's so many different kinds of rockets, many, many different kinds, and they're all made a little bit differently. Some are made a lot of it differently. So I had to pick one in order to figure out how to kind of walk through the process. And as I did some research on this, can you believe it that it's really hard to find exact information on how rockets are made?
Wow, that's so interesting.
Yeah, it's a little disappointing, but it also makes sense. There's a lot of work that's gone into designing this rocket and every other rocket, and these countries are competing against each other.
Yeah.
These companies are competing against each other, and you want to do better than your competitor.
Right.
If I'm playing chess against you and I figure out a good move, I'm not going to tell you, hey, you should do this, because that might, this is how I beat you. So there's competition between the companies and countries, but there's also cooperation. So there's a lot they can't say. We're going to talk about some stuff that we can say, because I couldn't find anything about what they couldn't say. So this is the main rocket we're going to be studying today. This is the Atlas V rocket. This is a great rocket. It is what has launched the last several rovers to Mars.
Wow.
Any of you who were watching my class 2 days ago, we talked about the Curiosity rover. We talked about Spirit and Opportunity rovers. All of those got to Mars on that design of rocket right there. Okay, what comes next? Oh, I have to give a big thank you to the YouTube channel Smarter Every Day. A lot of what we're going to be talking about, I grabbed screenshots from this guy's channel. This is Dustin Wilson Sandlin, and he was able to get a tour of the rocket factory in Alabama where the United Launch Alliance makes its rockets.
Wow.
So if you want more than what we're talking about today, you can find this video that I'm showing right here. This is how rockets are made from Smarter Every Day. This is very recent. This guy toured just a few months ago.
Oh, yeah.
And it's about an hour long. So I'm going to take parts of this and break it down so we can understand some of the more simpler, basic concepts.
Cool.
And I know I'm ignoring the Q&A section again. All right, Tanisha is asking, where are we right now? We are in Oregon.
We're in front of a rocket.
That's not a real thing behind us. It's a green screen. I don't know if you know that.
Really? No way.
Yeah, wait. So we're in Oregon. So we have Oregon and a whole bunch of other states and countries represented in this webinar today. Oh, Alette's asking a very important question. Is this what Isaac Newton looked like?
With a wig.
It's what one person thought he looked like. I think this is an actual portrait of him done.
Really? That's not a wig?
When he was alive.
Oh.
It might be a wig. But that seems about right to me. I didn't know him personally, so I can't talk about that. So huge thank you to this channel and to Dustin for getting this tour of this rocket factory. A guy that you're going to see a lot throughout these photos, these screenshots that I took, is Tori Bruno, who is the president and CEO of this company, United Launch Alliance. They make the Atlas V rocket that we're going to be learning about. They make the Delta IV Heavy, which we talked a little bit about in our webinar the other day, and a bunch of other rockets. They have a ton of experience in getting to space safely. The Atlas V rocket is going to be launching the Mars Perseverance rover in just a couple of weeks. And they're calling it the Mars 2020 rover because this is going to be their 20th payload that they've delivered to Mars.
Wow.
So this company is very good at what they do. Okay. So their factory is here in Alabama, and they build the rockets there. Parts are made all over the place. Some of the engines are actually designed and made in Russia and sent to America. Many of the parts are built all around America, sent to this central factory in Alabama, and then it goes on a barge up the river, down the river, into the Gulf of Mexico. And then there's two main launch locations in America. You have Cape Canaveral in Florida.
Yeah.
And that's where we launch for things that are going to be orbiting the Earth more around the equator. But sometimes you want to launch from over here on the West Coast from Vandenberg Air Force Base. And that's, they'll launch from there when they're trying to get something that's going more north-south instead of east-west because of science.
Cool.
Yeah.
And why is it that they have to transport the parts like that?
Well, rockets are big, right? You look at this gorgeous space shuttle behind us, you can't fit one of those side boosters on a semi-truck. Well, okay, so I have to correct myself there. SpaceX does ship their rockets by truck.
Wow.
Final assembly and putting all the Lego pieces together happens at the launch site, but they'll make their main rocket and then they'll stick it on a really powerful truck and drive it across the interstate.
Cool.
So, but water is a great way to transport heavy stuff.
Right.
So both ways are good, you know?
Cool.
At the beginning of this factory, they bring in these giant sheets of metal. And what we see here are 2 sheets of aluminum. You can see how thick they are at the beginning, right? It's absolutely massive. You'll see some pictures of these. And so that's what it looks like from the edge. And there's they put their factory really close to this steel and aluminum mill. So they basically just drive this stuff across the road and drop it off at the factory.
Cool.
You can see, here's a picture that shows about how big these things are. This is after it's gone through a bit of a carving process, and we'll see how they carve it away in order to make it good for spaceflight. But these guys are going over, they're cleaning it, and they're inspecting with their own eyes every inch of this to make sure that nothing went wrong in the carving away process.
Wow.
Imagine that's your job. Like,
yeah.
I inspect rockets.
That'd be cool.
That would be
Tiring,
super
but
cool. Yeah, I would be very proud to have that job. So that they start with that giant slab of aluminum, and they go through with these very fine drill bits, computer-controlled drill bits, and they carve away that aluminum. More than 90% of that aluminum gets cut away into these little tiny metal shavings, metal chips. And they collect all that leftover metal, and they ship it. They send it right back across the street to the factory or to the mill, where they then just melt that aluminum down, turn it into another big slab, and send it back. So they carve away most of it to leave this, what's called an isogrid. A grid just being a group of something that repeats. It could be a grid of squares, or a grid of rectangles, or a grid of like hexagons, like in a beehive, right?
Is there a reason why these are triangles?
Yes.
Oh, cool.
Perfect. So this is called an isogrid. Iso means equal. A triangle is a very, very strong shape. You'll see buildings that are designed to withstand earthquakes. You'll see triangular designs in their supports. Because let's say there is some stress, some force that's pushing this way along the grid, right? The force arrives here, and then it's spread out into these other triangles. It kind of disperses everything.
I see.
So rocket launches are violent. There's a lot of force, and you don't want your rocket falling apart. You can't really have any weak points in there. So this helps take any motion, any force, and just kind of even it out a little bit. This grid was designed at a time when this was the best they could do. They did all these, someone that really knew their math and science, they figured out this is the best way that we can have the strongest thing for the least amount of weight. Weight is super important in rocket launches. You want it as light as possible, but it needs to be strong.
Yeah. How much does a rocket weigh on average?
Not that much. I don't have that in my slides.
Okay.
Yeah. Most of the weight of a rocket is not in the structure itself. It's not in the metal. It's actually in the fuel.
Oh.
But every pound that you add to the rocket itself makes it harder to get up. Here is the machine that's cutting it away. I'll say it's at least 1 to 2 million pounds.
Wow. Okay.
I'm totally just trying to remember stuff that I saw the other day, okay? So I could be way off, but I can tell you it's not 10 pounds. It's not 100, and it's not 100 million. It's somewhere between 100 and 100 million. I can tell you that with absolute certainty.
Nice. Maybe you guys can look it up for me later.
Yes. Oh, Q&A section can help us out here. Okay?
Oh, yeah.
Good. Taryn asking a great question. How long does it take to make the Isogrid? I think I noted that down. Hang on just a second. You're hired, man. Takes 2 days.
Wow.
It takes 2 days to carve out that. There's a new kind of grid that they're making. So here is the machine in process. There's water all over the place in order to keep the temperature down. You don't want to accidentally melt the metal. And you can see this is not an isogrid. It's not triangular, it's rectangular. And this is a new design that they're starting to implement. That they figured out a whole new set of calculations and stuff was done in the 90s with better tools, better materials, better programming, better everything. And they figured out they could make it what's called an orthogrid, ortho meaning straight or rectangular. And this takes half the time to make. So this takes 1 day to carve out one of those panels instead of 2. And it's lighter, which is great. And it's actually stronger.
Huh. How come it's stronger than the triangular shape?
Because science.
Wow, okay.
I can't give you a great explanation of that because I don't have enough training on that myself personally. But these guys, these literal rocket scientists say that. So I'm going to take their word for it.
Cool.
When there's someone that studies decades in order to become an expert at something, I tend to listen to them.
Yeah, makes sense.
Not all the time, but I tend to. So here is a picture showing, there's Tori Bruno. You can see just how massive that piece of metal is. So again, this piece of metal rolled into this factory, one giant slab, and then they cut away more than 90% of it in order to create that grid. All right. What's next here? And then they take that and they put it in this giant press that bends it very, very carefully and gently. It bends it into a curved shape. And several of those will be fused together to make the cone of your rocket, or to the cylinder of your rocket, or to make fuel tanks inside. What's the next one here? Oh yeah, I want to talk about this really quick, but I'm not ignoring the Q&A section. Okay, so Arnav is asking, why do rockets use fuel? Why not electricity? So yeah, that's an excellent question. I'm going to rewind. Because in order to go up, you need to send something down, right? Electricity is useful for moving many things. You have electric cars, right? And you have an electric car and you can use electric motors to spin the wheel. And that makes the car go forward. But the car is able to go forward because the wheel on the ground is pushing backwards. The wheel pushes that way, and that makes the car go that way.
And so that's why we can't have electric cars, but can't have. Okay.
That's right, because the electricity, with an electric train or an electric plane or an electric car, that electricity is being used to send something one way so that your vehicle goes the other way. You still need to send something out in order to go up. So you have to use fuel, rocket fuel.
Do you think they'll ever be able to make electric rockets?
Well, what's it gonna send out? You know?
Air? Like really concentrated air?
You could do that. That's essentially a jet engine,
Yeah.
right? A jet engine still uses fuel, right? But a jet engine takes air, compresses the air super tight, and then puts a bit of fuel into there. Air blows up. You move forward. But there's no oxygen in space. There's no air in space, so you still need to take your fuel with you. But Arnav, you're asking a great question, and Ananya, that's an awesome question. Is there a way to be far more efficient?
Yeah.
And use less fuel to get more stuff done?
Yeah.
Probably. Okay, Tanisha's asking, when were these pictures taken? So as I said at the beginning of this class today, most of the pictures today are screenshots from this YouTube video from the Smarter Everyday channel, where he was able to tour with the CEO of the United Launch Alliance, their factory. Okay. Yes. Sam says, remember Wally when he used the fire extinguisher in space? It's just like that. Exactly.
Yeah.
Exactly. I almost put a clip of that scene in this slideshow today. He took a fire extinguisher.
Yeah, right.
And he shot the fire extinguisher, and white fire extinguishing stuff went that way, and Wally went that way.
Yeah.
That's exactly correct.
Really smart, Sam.
Yep. Okay, so Tarun asked a bunch of questions. Some of this is covered, Tarun, in the coming slides. And whatever I don't answer in the coming slides, I will answer in the Q&A section at the end of the class. So moving on, oh yeah, here we are going forward. Look how happy this guy is. He's just talking about rockets, okay? Super cool. So after you take that aluminum, you carve it out in order to get your grid, and then you bend it into the shape you want, aluminum is going to rust. Mm-hmm. Aluminum is going to erode eventually. And if that starts happening, it weakens it. So they put it through a series of baths in order to strengthen it up. And it's a certain kind of acid that they put it in. Mm-hmm. So they dump it in this giant pool of acid. They heat up the acid, and they run a bunch of electricity through the acid. Oh. So it's not great for humans. I do not recommend this. You will die 3 different ways. But it's great for aluminum. So they dump it in the acid, and then they rinse it off in water, and then they do it again, and they rinse it off with water. And you can see, here's before, here's as the aluminum's going into the acid bath, and here's as it's coming out. Ooh, isn't that pretty?
Yeah. It's so satisfying.
It's so satisfying. I would love that job too.
Yeah.
Just to make pretty metal, pretty space metal. Now, take a look at this section of the rocket here. Oh. It looks kind of coppery, right? Mm-hmm. After this process with the aluminum is done to make it this nice, rich white color, it actually begins to naturally take on a coppery color. And that's just, there's some chemistry behind it. I chose not to go into that today. Other rockets don't look like this because every rocket's made a little bit different. Everyone tries something a little bit different because there's more than one way to do it.
Yeah, for sure.
So who knows, I'm glad that we're trying new ways.
Yeah.
That's how we figure new stuff out.
Yeah, and just a question, does the chemical reaction that turns it into that coppery color have anything to do with the actual function of the rocket, or is it just something that happens?
It's just a side effect of something that happens.
Cool.
Yeah, I don't want to get into that today, but it's super interesting.
Cool.
This is a great subject. Why does aluminum turn coppery after an acid bath? Feel free to research that. Sam said, you said you'd die 3 different ways, and I thought of a supervillain.
Yeah.
Yeah, I would make a good supervillain.
You really would.
Thank you.
You have low-key supervillain vibes.
Thank you.
Yeah.
Jacob asking the real questions. Was the Atlas V rocket made with an Isogrid or an Octogrid? Great, Octogrid or Orthogrid. The Atlas V rocket that you're looking at there, that's with the Isogrid.
Okay.
So it's got the triangular stuff inside.
Mm-hmm.
The United Launch Alliance is working on the successor, the next rocket after the Atlas V. They're going to call it the Vulcan, which is super cool.
That is really cool.
Right?
Whoa.
And the Vulcan, it takes all the lessons from Atlas V and takes everything that we've learned since then and combines them.
Cool.
So the Vulcan is very much like an Atlas, but it's got the Orthogrid, that rectangular. Lighter, stronger, more powerful.
Cool. And have there been any rockets made with the Orthogrid yet, or is this going to be okay?
Plenty, yeah. And they've been testing, I don't know if anything from the United Launch Alliance has launched, but they've definitely been testing out this new grid. We've known about it since the 90s. We've known since the 90s that the Orthogrid is a better, more efficient, stronger design than the Isogrid.
Mm-hmm.
But the Atlas V rocket was designed and already perfected by that point. And when you have a rocket that you know launches, and it launches really well, and it like never fails, you don't change it.
Yeah, that
right?
makes sense.
I know something is better, but this is perfect as it is. So.
Okay, Evan says the acid is called chromic acid.
Yeah, there you go. Oh man, we have some smart cookies watching today.
Definitely.
All right, smart cookies. We're going to learn a little bit about welding, okay? Did you know you were going to learn about welding today?
No, I really did not.
Welcome to my class. So you might be familiar with this type of image here, right? You have two pieces of metal or other material, usually metal, that need to be fused together. They need to be welded, joined together. Because if they're apart, what are you going to have your rocket do fall apart when you launch it? No, it needs to stick. They don't use Elmer's glue.
Dang, that was my first guess.
They don't use paper clips or Scotch tape. They need something a bit stronger, more than super glue. So you can take metal, here's one piece up here, here's another piece down here, and you can take some third metal and heat it and melt it and put it between the two and join them together, right? Think like hot glue, a hot glue stick, right? You melt the thing and you put it on there and it sticks the two parts together. That's a great way of sticking two pieces of metal together normally.
Yeah.
When you're working with rockets, there's just so much going on. It's better for it to be stronger than that. So what was my next slide? Yes. So instead of taking, here, I'm going to pop out here. Boop, stop share. Hello, rocket. Let's say I need to join these two pieces of clay together, right? When these launch, they're just going to fall apart. So I want them to be joined into one piece. If we were to weld like we were looking at there first, I would take these two pieces and I would melt some clay, or call this metal, and I would put it over them like this and it would stick them together. And it would stick, and then I'd continue that process and so on. And we would have two pieces of metal clay fused together.
Yeah.
But it's not the strongest way to do it necessarily. And there is another way that they found that is stronger and that doesn't add more material. Again, weight is super important.
Right, right.
We just spent days covering away 90% of the metal, right?
Right.
So the more you add, the heavier it gets. And that's a problem. Well, they found, all right, everyone take your hands, put them together, rub. Starting to heat up, right?
Yeah.
Starting to get hot. Same thing happens with metal. Two things, when you rub them together, they get hot. And you can heat up the metal to a point where it doesn't melt. You don't want to melt the metal because that'll start to weaken it, but you can make it kind of gooey. It's not quite melted yet, but it's that perfect level of marshmallow where it has all its properties, but it's not liquid.
Huh.
And you take that and you heat up the metal and you spin. There we go. Boop. So this bit so here's one piece of metal over here, and here's another piece of metal over here, and there is the joint, the seam, the area where the two of them are separated. And this thing comes down, it spins super fast, and it spins in a circle, and the friction of that spinning on it warms up the metal, doesn't melt it, and it combines the metal together. It stirs it up. This is called stir welding, like stirring a pot of soup. So if I were to take this metal clay and just kind of stir the material together, I hope this is showing up well. To just stir it together to make, this is a really bad demonstration. Okay, it shows it shows what's happening. It's not very strong here, but if you were to kind of push it back and forth, so it really becomes one piece instead of two pieces, that did not go as I planned.
Well, yeah.
But it works for rockets, okay? I have some paper here to wipe my hands on. But it works for rockets, and you can use that to take those different pieces you've been working on and to fuse them together into one very strong thing. So here you have, there's Tori Bruno, and here's, I keep forgetting his name. I'm so sorry, Destin. Looking at, this is a fuel tank that they're making. So you can see there's the seams where they use that welding technique to join it together. And we can see this now looks very familiar to us. This is an isogrid on the inside. You can see the triangles there, triangle, triangle, triangle. They were gonna take caps, domes, and put them on the top and bottom, and you'll have a very strong tank here that you can fill with liquid oxygen, you can fill it with rocket fuel, and stick it inside a rocket, send it to space.
Cool.
Max is asking, are we going to talk about the Falcon 9? A little bit, but it was a lot harder for me to find videos and photos of the Falcon 9 while it's being made. I don't blame them for guarding their secrets very closely. I would probably do it too if I was making my own special rocket. We can talk about Falcon 9. A lot of people asking about Falcon 9. Excellent. When does this class end? Technically in 5 minutes. But Tanisha, you've been in my classes before. You know I always run late. So there we go. Here is a great photo. Here you see the outside of the rocket there. That outside shell is made through the very process that we were just talking about. And you can see there's the seam of the welding right there. Whoop. And then on the inside, you can see that Isogrid are really nice, fancy triangles there. And inside, there's the top of a fuel tank.
Wow, that's a gigantic fuel tank.
It's a gigantic fuel tank. You can stand inside it, and you know, there's probably really good acoustics in there. You can sing, right? That's what I would do with a rocket.
Definitely.
The fuel tank and the outside of the rocket are made using the same process. They just make the fuel tank a little bit smaller so they can fit it inside the rocket. Okay, now we're going to talk. That was all about the first stage. That's just the part of the vehicle. We're just talking about this section right here. It only flies for a few minutes, and then the top half of the rocket flies off the second stage, and it does its own thing, and this crashes back to Earth. So let's talk about the rest of the rocket, the second stage. Boop, boop, boop. The second stage is not made out of aluminum. It's made out of stainless steel. You all probably have knives in your parents' kitchen that are made out of stainless steel. It's strong. It doesn't rust very easily, but it is heavier than aluminum.
Okay.
So
You can't make the whole thing out of it.
you could, but it's going to be a lot heavier.
Right.
Right? And it's a bit more expensive as well to use the stainless steel, and it's heavier. So heavier, more expensive, not great. And if you're only going to use it once, it's not a good business model. It's not very efficient. That second stage is going to have a lot more use than the first stage. So you can use stainless steel up there because it's just better for that second stage. Here you can see this is part of a fuel tank that they're making here. This doesn't even show how thin that steel is rolled.
Yeah, I mean, you can kind of tell, but
you can kind of tell.
Yeah.
That is half the thickness of a dime.
What?
It is super, super, super thin. They don't carve this into the Isogrid or an Orthogrid because it's so thin. Half the thickness of a dime. They figured they can go that thin. But when you have it in a spherical shape and fused together strongly, that nice spherical shape is great at storing liquids and gases at high pressure. So here you have part of a second stage. You can kind of see part of it here. They've started to add some of the equipment around it, right?
Yeah.
But you can see there's the metal kind of cap to it. This that we're looking at right now is the part of the rocket that is going to be sending the Mars 2020 Perseverance rover. 2020, right? And I couldn't get a lot of details on what do all these pipes mean and what is this covering and where do you put all the computers and stuff like that. That's really not publicly available, not that I could find. So that's fine. Hey, companies are, they're welcome to their very well-earned secrets. Here's a picture of the part of the factory they're making. There's the Mars 2020. This is for something else, I forget. And they're building this. This has 2 engines on it. This is intended to send humans to space station or maybe moon, right?
Oh, cool.
We're a little low on time here. Yeah, we're running out of time. So I'm going to catch up on the questions, power through the rest of my slides, and only run a little bit late. Okay. Jacob's asking, how many years does it take to make a rocket? So to develop a rocket, to figure out, hey, this is a good way to make a rocket, many years. 5 to 10 sometimes. Other rockets have taken a lot longer to figure out.
Yeah.
NASA's been working on a new rocket called the Space Launch System. And they've been working on that for 20 years, 15,
Wow.
maybe 10, 15, maybe 20 years. Running into a lot of problems on that one. There's a lot to figure out. SpaceX developed the Falcon 9 in about 5 years.
Oh.
NASA developed the Saturn V that we used to launch the Apollo missions to the moon in, I think, 5 years. I would have to guess 5 years on that one. But they were taking all the lessons from all the earlier rockets that they were making. So really, the Falcon 9, you could say they designed the Falcon 9 and made it and all that in 5 years. But actually, the design for the Falcon 9 started in the 1930s with the very first rocket designs.
Yeah.
It's all one process.
Yeah.
It's just the latest version, right? Okay.
That is so thin. Yes, it is.
Super thin. Yeah. Tanisha's asking, what's the shortest amount of time to make a rocket? That's a great question. I mean, you could do it quick and dangerous, or you can do it slower and safer. And April says we're officially out of time. Yep. But I'm not done. All right, classic James fashion. Here we go. Oh, there's a closer photo of, so this is the second stage. This is what goes on top of the main part of the rocket. This fires off, and there's 2 engines there in order to get a better, bigger, stronger push out to space station or the moon or potentially Mars, right?
Cool.
Last thing I want to talk about is the very top of the rocket. the thing that you're launching, let's say you want to launch a satellite, you want to launch a spacecraft, a thing, that's called the payload. It's what you're delivering. And around the payload is something called a fairing. And every rocket's going to have this on the top, something like this. And it's a shell that protects the spacecraft during launch. And here it is closed. I promised we were going to talk about SpaceX. And here's it as it comes open like that. It just pops away, and now the spacecraft is open to space. It's able to do its thing. As soon as the rocket's out of the atmosphere, the fairings come off.
Wow.
Because they weigh something.
Yeah.
And when there's no air, there's no reason for a fairing. So they pop them off, and the whole rocket just got, thousands of pounds lighter.
Right.
Here's another picture. This is an Atlas V fairing. So there's a satellite or, a very fancy can of tomato soup or something like that. Looks like that to me. And here's the fairing that goes on the outside of it to protect it. And here's a picture of as soon as it's out of the atmosphere, it just pops off. Boop.
Nice.
Now, the fairing is not made of aluminum. At least not anymore. Maybe it was at one time, but not anymore. And it's not made of stainless steel. It's made of a third material that we're going to talk about super quickly here. Oh no, James, what are you doing? Big words. Carbon composite. Carbon is a natural element found all over in nature. It's very strong. Coal is carbon. Diamonds are carbon.
We're carbon to some degree.
We have carbon all up in our body. So it's available all over the place. Very, very strong element. And a composite is just a thing made up of several parts. So some smart dudes, people, years ago figured out you could take carbon fibers, like strings, like threads of carbon, and kind of weave them together into a very, very strong material. It's light, it's strong, and you can make it kind of any shape you want, which is great when you need a very specific shape like that on your fairing, right? You want that nice curved nose there and some straight edges and some bends and stuff. So why don't use carbon composite for the entire rocket? Because it's super expensive.
Makes sense.
The process for making it is not as easy as the rest. It costs a lot more money. Each of those, so SpaceX figured out they could save millions of dollars per launch if they could catch these fairings after they're separated and reuse them.
Smart.
They tried for years to catch the fairings, like 2 years. They tried and failed, tried and failed, tried and failed. I won't even say failed. They tried and learned how to not catch it. And they tried again and they learned how to not catch it again. So now they have these boats with these giant nets, these nets of the size of like soccer fields.
Oh.
And they fly, they sail out into the ocean under the fairing, and they catch it in this giant net.
Oh.
And it saves them, I think they can save $6 million per fairing half per launch.
Per fairing half.
Per half. So they
so
catch both halves,
total.
you can save $12 million per launch. So, hey, it's a lot of money.
Yeah, for sure.
Okay. So could you build your entire spacecraft not out of aluminum, but out of stainless steel? It's stronger, right?
Heavier.
It's a bit heavier, but it's way cheaper in some ways. So the steel is going to last a lot longer than the aluminum, but it is heavier. But SpaceX was like, what if we didn't use a rocket only once? What if we used it 100 times? If you could make it, most of the cost of a rocket launch isn't the fuel, it's building the rocket. We just talked for more than I was supposed to talk about what it takes to build just one part of the rocket. What if you could reuse that and just put more fuel in it?
Yeah.
Clean it up, refuel, launch again.
Right.
You save a lot of money.
Right.
But then you have the problem of your aluminum rocket would start to fall apart quicker than you want, or get weaker before you wanted it to. Stainless steel, I've had the same set of stainless steel knives for the last 15 years.
Yeah, my parents too.
Yeah. It can last a long time. It can withstand a lot of punishment. So here's a concept for SpaceX's Starship. And it's made entirely out of stainless steel. It's very shiny.
Yes.
It's a very
shiny.
pretty rocket. It's very shiny, very kind of like sci-fi rocket concept.
We're getting there.
Yeah. So it's a lot heavier, and so it's going to take more fuel to launch it. But their idea is that you could launch this same rocket 100 times. And over time, it's going to save a lot of money. I would rather have that than lighter, cheaper rockets to make that can only launch once.
Right.
So I'm definitely out of time, way out of time. If you have more questions, other topics that you'd like to cover in space science, online learning at Delphian.org is where to send those questions and concepts and ideas. We have 2 more space science classes coming next week. I have not decided what we're going to talk about. Totally up in the air. So if you have an idea, send it to me at this email address, and I will see if we can cover that. One last question that I will answer from the Q&A section. Why do people even go into space? Well, Tanisha, yeah, because it's fun. And because, like I said, humans want to explore. We want to find out what's next. You know, you want to find out if I point to something over there behind the camera, I'm like, look at that, and you can't see it. I'm actually being really mean to you right now because now you want to know what I just pointed out. Do you see that thing?
Yeah.
I want to know what it is. Right? So you look into space, you can only see so far. You're like, I want to go there. I want to explore and learn. That's why we go to space and climb mountains and dive deep into the oceans and all this stuff. Okay. I'm going to stick around in the Q&A section, answer more with typing than I can by words. Ananya, thank you so much for joining me today.
Yeah, it was so fun. I learned so much.
I'm so glad. I know you didn't get to talk a lot. And in next week's classes, I'm going to try to have you teaching me some stuff as well.
Ooh, okay.
Right?
Okay.
So this is school. We learn. That's okay. And a good teacher learns from their students all the time. Thank you very much, everyone. We'll see you next week.
Bye, guys.